When we talk about machine learning, that word learning can be a little bit tricky because the real goal, the absolute heart of the entire field, isn't just about learning from data, it's about generalizing from it. It's about how well a model can take what it's learned and apply it to brand new situations it has never, ever seen before. And that, right there, is the biggest challenge we're going to tackle today.
So this really gets to the core of the problem, right? How do we actually know if a machine is truly learning, or if it's just, memorizing? Think about it like this. You've got a student who crams for a test, memorizes every single answer on the study guide, and then aces it. Do they actually learn the subject? Probably not. And that is the exact same dilemma we face in AI. We have to figure out if our model is a real learner or just a really good memorizer.
Okay, so how do we tell the difference? Well, we use two really important numbers. First up, you've got your training error. You can think of this as the pop quiz on stuff the model has already seen in class. A low training error is great, but all that really tells you is that the model is good at memorizing the answers. The real exam, the final, is the test error. This is where we show it brand new, unseen data, and that is the true measure of learning. See, the goal isn't just to ace the quiz, it's to actually master the material.
Right, and this is exactly where things can get a little dangerous. If you only look at that in-class performance, that training error, you can get a totally false sense of security. It creates this powerful illusion. You think you've got an A+ student, but in reality, that model is completely unprepared for the real world.
So here's the bottom line. A model's real-world performance really comes down to two things. First, you absolutely have to make that training error small. The model has to learn something from the data. But, and this is the big one, you also have to make the gap between the training error and the test error as small as possible. If that gap gets too wide, you haven't built a learner, you've just built a memorizer.
And this whole balancing act, it throws us right into the middle of this classic tug-of-war in machine learning. Underfitting on one side and overfitting on the other. And the rope they're pulling on, well, that's what we call model complexity, or its capacity.
So you might think, okay, this seems pretty straightforward. As we give a model more capacity, basically make it more complex and powerful, its error on the training data just keeps going down. I mean, it makes sense, right? A more powerful tool can fit the data it's already seen almost perfectly. So the more complex, the better, right?
Well, not exactly. This is where that illusion we talked about completely shatters. Now, look what happens when we add in the generalization error. That's the performance on new data. It makes this classic U-shape. At first, things are great. More complexity means less error. But then you hit this sweet spot, this optimal capacity. And after that, things go south. More complexity actually starts to hurt performance. The model gets so powerful it starts memorizing random noise, and the generalization error shoots back up. That growing distance between the two lines, that's the dreaded generalization gap.
Okay, so let's look at the left side of that U. This is what we call underfitting. This is pretty simple. Your model is just, well, it's too simple for the job. Imagine trying to capture a really curvy complex shape using only a straight ruler. It's just not going to work. The model fails to pick up on the real patterns, so it's bad on the training data, and it's bad on the new data. It basically hasn't learned anything useful at all.
Now let's jump over to the far right side. This is the exact opposite problem, overfitting. Here the model is too complex, it's too powerful. It doesn't just learn the important underlying signal, it ends up memorizing all the random noise, every little quirk and irrelevant detail on the training data. So its training error looks amazing, it's super low. But the moment you show it new data, it just completely falls apart. Why? Because all that random noise it memorized, it isn't in the new data. It fails, and it fails spectacularly.
Okay, so if we know that too much complexity is the enemy and too little complexity is also bad, how do we find that perfect balance? How do we fight back against overfitting? Well, believe it or not, the answer comes from a philosophical idea that's been around for centuries.
And that principle is the famous Occam's razor. The core idea is just beautiful in its simplicity. It says that if you have a bunch of competing explanations for something, all of which seem to work, you should probably choose the simplest one. Don't make things more complicated than they need to be. And for us in machine learning, this isn't just some dusty old philosophical idea. It's a practical, powerful tool for building models that actually work.
So how do we actually use this idea? In machine learning, we have a whole toolbox of strategies called regularization. And you can really think of regularization as just Occam's razor put into code. What we do is we add a sort of penalty during the training process. The more complex the model tries to get, the bigger the penalty becomes. It's like we're telling the algorithm, hey, I want you to explain the data, but I also want you to be as simple as you possibly can be.
This forces it to focus on the real important patterns and ignore all that distracting noise.
All right, all of this whole balancing act, leads us to a really deep, fundamental truth about AI. And it's this: there is no magic bullet. There is no single, one-size-fits-all algorithm that is just the best at solving every single problem you throw at it.
This isn't just a hunch either. It's actually a formalized concept called the no free lunch theorem. And what it basically says is that if you were to average the performance of every algorithm across every possible problem in the universe, they'd all come out the same. An algorithm that's an absolute rock star at identifying cats in photos might be completely useless for financial forecasting. There's just no such thing as a master algorithm. So what does that mean for us trying to build things in the real world? It means the game isn't about searching for some mythical perfect algorithm. Not at all. It's about being a smart engineer. It's about, first, really digging in and understanding the problem you're trying to solve. You have to know your data. Then you design or pick an algorithm that's tailor-made for that specific data. You build in the right preferences, like a preference for simple models, using regularization, to get the job done right.
And this leaves us with a huge, kind of fascinating question to think about. If this no free lunch theorem is true, if specialized tools are always going to outperform general ones, what in the world does that mean for the search for artificial general intelligence, or AGI? It kind of suggests that the path to a truly general AI might not be about finding one single brilliant master algorithm. Maybe it's about building a massive, complex ecosystem of thousands of specialized learners, all working together. Now that is something to chew on.